What would you do if someone handed you two equations at once and said, find the solution that works for both of them at the same time, and do it by graphing? I'll tell you what I'd do. I'd graph the first equation, graph the second equation, and say, I've got it. The point where the lines cross satisfies both equations. And what if the lines didn't cross? We'll see about that in a minute. But first, a quick review of all this business of equations and graphing right from the beginning. One equation in one variable usually gives us one solution, which we can locate exactly on a number line. It's possible, of course, to work out one equation with one variable and get no solution at all. Or we may get too many solutions. Here, the answer is meaningless because every answer is right. But we know that we can simplify and solve all those equations that can be solved by applying the same operations to both sides of the equation: addition, subtraction, multiplication, division. If you have any questions about that, review the modules on linear equations. When we looked at equations in two variables, we found a different situation. One equation described an infinite number of points along a straight line, so we graph it just like that. And now we face the question we saw at the beginning of this module. How do we handle two equations at the same time? Same question. How do we handle a system of simultaneous equations in two variables? I've already told you the answer, but now we're going to approach it step by step, because plunging in doesn't work. For example, I can grab hold of an answer that works for the first equation, x equals 4, y equals 0. But it doesn't work at all for the second. Check it out and you'll see. Or I can grab an answer that works fine for the second equation, but that one won't work for the first. What we want is one that will work for both at the same time, a set of xy coordinates that will satisfy both equations. Let's start by graphing the first equation. If you've forgotten how to do that, you'll need to review the module on straight lines before you continue. Here's the graph of our first equation, a straight line along which every point satisfies the equation. Question: do any of them also satisfy the second equation? Answer: look at the second equation and let's find out. We get the points we need in the same way as before. We work out our second graph, and then we simply add it on top of the graph of our first equation. The point we're looking for is the point where the two lines cross. We read off its x and y coordinates, and we have it. An answer that satisfies our system of equations. We can check that by substitution, of course, and we get exactly what we expected. The solution is true for the first equation and true for the second at the same time. It works. Can you do it yourself? Of course you can, and here's a chance to prove it. Plot the graphs for these two equations. Find the point where they intersect and name the coordinates at that point. I don't have any trouble at all plotting the first graph, except that my 2 points are fairly close together. X is 1 and y is 1/2. Then I do the second equation and come up with 9/2 for x and -3 for y. I drop the one on top of the other and find that they cross at a point that looks like 3, -1. Of course, I can't really tell just by looking whether x is precisely 3 and y is exactly -1. What can I do to be sure? Substitute, of course, and see if it works. That way, I don't have to rely on the graph. There are also other methods involving substitution or elimination, which we'll handle in other modules. So far, so good. We plot the two graphs, they cross each other, and we find the point at which they intersect. What about when they don't intersect? There are several possibilities. The graphs may be parallel lines, they don't cross, and there is no solution for us to find. It's easy to recognize a system of equations like that because the two lines have the same slope. If you have questions about slope, check the module on equations of lines and slope. Another thing that can happen, you have two equations like these. You graph the two lines and discover that one lands on top of the other. They are in fact the same line. We call these two equations dependent. Any point on the line satisfies both equations, so there are many solutions. You can use these ideas to solve any problems that produce simultaneous equations in two variables. But you're going to find that the method works best for equations with integer answers. There are lots of problems like that in your book. You'll want to study some of them to get used to the whole idea. And you'll want to think about using this technique on word problems, too. Like this. Your friends go to the used books and records store. They find super savings, one price for all the records, one price for all the books. Each buys a different combination of books and records. But they pay the same one price for each book, and they pay the same one price for each record. What are those two prices? First, we translate from English into algebra by naming our two variables. And then writing the equation for Joanne and writing a second equation for Gary. Simple enough, we have our two equations. We solve the first one to find 2 points so we can graph the line. We solve the second and find 2 points for that line. We seem to have lots of fractions, but we just figure out exactly where the points belong on the two axes and go right ahead and graph our two lines as accurately as possible on the same plane and read off the coordinates of the intersection. It looks like x equals 2 and y equals 3. But we check by substitution just to be sure. For the first equation, it works. For the second equation, it works. We've got it. We know that the books cost $2 apiece and the records cost $3. Now here's one for you. Name the two variables, translate the problem into algebra, draw the two graphs, read off the point where they intersect, and come back with your answer. It doesn't really matter what letters I use for the cost of raisins and the cost of mushrooms, as long as I'm perfectly consistent. To make it simple, I stay with x and y, and I translate into the two equations, find my points, and plot the two graphs like this. I read off the intersection as x equals 1, y equals 2. Test it by substitution and find that it works. So we know that raisins are $1 a pound and mushrooms are $2. Incidentally, you can solve this kind of problem without graphs if you like. You'll find that in the modules on solving by substitution and by elimination. But for now, you'll want to concentrate on this method by handling some of the problems in your textbook. Good luck.